In this video, we're going to talk about a basis for a topology. So we know that a topology tau for a set X is the collection of all open sets in that topological space. And that collection of open sets can be large and complicated. So for example, if we try to describe all open sets in the real numbers with the usual topology means generated by the metric, by the usual metric. Distance between x and y is the absolute value of x minus y. So if we think about that metric space, which is a topological space, we know that the open balls in that metric space are of the form x minus epsilon to x plus epsilon, those open intervals. And we showed, therefore, that any open interval is in fact open. A comma b is open for a less than b in the usual topology. And because those sets are open, arbitrary unions of those sets are open, so we could take some strange, union of things like the union of I to I plus 4 from I equals 1 to 7 together with union negative pi to pi together with the union of like negative 507 to 506. So, we could just union arbitrary open intervals together and that will also be an open set. But we're just describing some open sets. We're sort of saying what they look like in general. We're saying they're arbitrary unions of open intervals. And so that kind of gets to the idea that, well, maybe that sentence, arbitrary unions of open intervals, is more the kind of thing we want to talk about when we talk about what's in a topology. So that idea gets us to the idea of a base or basis for a topological space. So collections of open intervals, for example, or open intervals in the real line, that would be a basis for the topology we're talking about, sort of essential sets. And so our definition is that if x tau is a topological space, then a base or a basis beta for tau is a subcollection of the topology tau with the property that each member of tau is a union of members of beta. So as an example, R with the usual topology, an example of a basis would be beta equals A comma B, such that A is less than B are elements of R. That would be a basis for the usual topology on R, because any open set in the real numbers with the usual topology is some union of elements of that form. That each member of tau is a union of members of the basis. The members of a basis are called basic open sets. So any open interval with this basis would be a basic open set, and tau is also called the topology generated by beta. So how can we verify that a collection of open sets is in fact a basis for a topology? So we stated this above, but we'll also verify it using the theorem below, that a family beta of open subsets of X is a basis for the topology tau on X, if and only if, for each X in X and each open set U containing X, there is a basis element B in beta such that X is in B and B is a subset of U. So we say that beta is basis for the topology tau on X if for any X in the big set X and any open set U containing X, there is some, there exists some B such that B contains X and B is a subset of U. So let's prove this theorem. Going in the forward direction, suppose that beta is a basis for tau on X. Then let's let X be an element of X and U an open set containing X. Since beta is a basis for our topology, for the collection of open sets. That means that U is a union of some sets from beta. So U is a union of sets from beta. So U is equal to a union of sets from beta. X is an element of U. Therefore, there is some B in beta, some set in that basis, such that X is an element of B and B is a subset of U. Now going in the reverse direction, suppose that for each X in X and each open set U containing X, it's the case that there is some B in beta such that X is an element of B, which is a subset of U. We're supposing the reverse. So we want to show that beta is a basis. Let's let U be an open set. In other words, let's let U be an element of the topology. And we want to show that U is a union of elements of beta. That's the definition of being a basis, that every open set in the topology is a union of open sets from the basis. So for each X that's in U, we know it's the case that there is some, let's call it B sub X in beta, such that X is an element of B sub X, which is a subset of U. And now we could observe that. So the union of these B sub X's, such that X is an element of U, would be our entire set U. And therefore, beta is a basis for tau. Let's now use the theorem above to verify that the collection of sets of open intervals a comma b, such that a is less than b and a and b are real numbers, is a basis for the usual topology on R. For this, we have to let X be an element of the set and U an open set containing X. Now let's think about this usual topology on R. We know that this is a metric space, and that because U is an open set containing a point in this metric space, there is some epsilon greater than 0, such that the ball centered at X of radius epsilon is a subset of U. This ball centered at X of radius epsilon is an open interval of the form X minus epsilon to X plus epsilon. So, this can be our A, this can be our B, where X minus epsilon, X plus epsilon are elements of the real numbers, and of course, X minus epsilon is less than X plus epsilon. So this ball centered at X of radius epsilon is an element of this thing that we're trying to prove is a basis, and X is an element of this set, and that is a subset of the open set U. So therefore, yes, we have verified that this is a basis for the usual topology on R, the collection of open intervals where A is less than B. As another example of a basis for a topology, let's say that X is any set with the discrete topology. So we know that in the discrete topology, every subset of X is open. Then one basis for this topology is the collection of singleton sets X, such that X is an element of X. That will be a basis for the discrete topology on the set X. Again, if we wish, we could use that theorem to verify. So let X be an element of X, U subset an open set containing X. Then, of course, X must be an element of the singleton set X, and that will be a subset of U because U contains X, and so we are done verifying that from the theorem. The collection of singleton sets is a basis for the discrete topology on any set X. One more example, any topology is a basis for itself. So if we've got some topological space X tau, then tau is technically a basis for tau. It's kind of a boring one, but remember, a basis has the property that any open set is a union of elements from the basis. And of course, U, an element of tau, implies that U is a finite union. U is equal to union of itself. So this is sort of just a boring version and kind of escapes the point of a basis. The point of a basis is sort of to simplify the idea of, what's in the topology. Let's think about it as the open sets that are generated by some basic open set, or some collection of basic open sets. But this does tell us that topological spaces can have more than one basis. So, the collection of all open sets is a basis for a topological space, as compared to, say, our previous two examples. Like if we're thinking about, say, the discrete topology, the collection of all open sets, that's every subset of the original space, whereas this other smaller basis is the collection of just singleton sets.